country.
Yes.
In India, this code is actually followed
Correct.
to design several kinds of steel structures.
Yes.
Okay, it
Yes.
may be column, it may be beams, anything.
Yes.
When it is made up of steel,
Correct.
it is actually designed with this code.
Yes.
Okay,
Yes.
whatever the formula we will use
Yes.
is given in this particular code, and we have to use this particular formula only. We
Okay.
can't use anything except this code.
Yes.
Okay,
Yes.
so this is the revised version of 2007, and
Yes.
after that it is not actually revised.
Yes.
So we will use the formula from here.
Okay.
So here you can see that here
Yes.
it is design of tension members. Okay,
Yes.
and it is starting from page number 32. So we will start with page number 32.
Okay.
First we will see some formulas, then we will move into the in your question,
Yes.
particular question.
Yes. So how many pages is this IS code? 8000,
It
2007,
is
800,
no, not much that. It is about 138. You can see here.
138.
Yeah.
Okay.
138.
Okay. So if you can send me that PDF, no, I'll get it printed.
Yeah. I will send it.
Yes. And so that RCC, for RCC, that 456 code is how many pages?
I actually don't know the particular pages, but it will be somewhere like this, like 150 or 160.
Okay. Okay, fine.
Okay,
That,
so these are the
yes.
parts.
Yes.
Tell me.
No, that code 456 also, that PDF, if you can send me, that will be a great favor.
That is also with me, but I
Yes.
will send you.
Thank you, sir.
Okay, so this is the table 5. This is very important. That
Yes.
is the partial safety factor.
Yes.
Whenever we will use the partial safety factor, we have to use from here.
Correct.
Okay.
Yes.
So these are the partial safety. I think you know the partial safety
Yes,
factor.
it is 1.5.
No.
It is gamma 0, gamma m.
Gamma m0, that is 1.1.
Yes.
And gamma m1, that is 1.25. That is basically for ultimate stresses.
Yes.
Whenever we will go for the ultimate stresses, and we have to use the partial safety factor for
Yes.
material purpose only.
Yes.
So we will use 1.25 for ultimate stress, and for resistance to member due to the buckling. Buckling means for columns.
Yes.
For columns, when we will use the strength of that particular material, like
Yes.
steel material.
Yes.
So we will use in that case 1.10, and for yielding again we will use 1.1. Okay.
Yes.
So these are the basic things that you have to use.
Correct.
This partial safety factor to calculate the exact strength of your material.
Yes.
Okay.
Yes.
Because we are using like Fe250. Okay.
Yeah.
You know about that Fe250 or Fe415 grade of steel, Fe500 grade of steel.
Yes.
So we are saying Fe500, that means that is the yield strength.
Yes.
Okay.
Yes.
Or I am telling you about the RCC structure, like Fe250, Fe415.
Yes.
But that is the yield stress, or but can you tell me that particular strength for that particular material is exactly will carry out in our particular structure? No.
No.
It will not carry out.
It will vary little bit.
Yeah, it will vary little bit. That is why we will decrease that amount of strength when we will go for design. That is why these partial safety factors are actually used.
Yes.
And similarly, in case of steel structure also, we will use this partial safety factor.
Yes.
Okay.
Yes.
So these are the different partial safety factors given here.
Yes.
And here comes your design of tension member. Okay.
Yes.
And for design of tension member,
Yes.
if you know that a tension member can be failed by 3 ways. Okay.
Yes.
In 3 ways, a tension member can fail. First,
Yes.
it is design strength due to the yielding of gross section.
Due to yielding, due to rupture, and due to block shear.
Yeah.
Yes.
So 3 things are there.
Yes.
One is due to the yielding of gross section.
Yes.
One is due to the rupture of critical section. And
Yeah.
third is due to the block shape. So this is your design strength due to the yielding of cross section. So you tell me that if a structure is failed by these three ways,
Yes.
and if we can resist these three loads.
So I didn't hear because. So one second, one second.
Okay, okay.
Yes, I'm back.
Okay.
Because the
So
dogs were barking, I didn't hear.
yeah.
Yes.
Okay. So if you have a steel structure,
Yes.
And if it is a tension member, then it can be failed by these three ways.
Correct.
And if we can resist somehow, if we can resist these three types of failure, then we can say that our design is complete.
Correct.
Okay.
That a design is
That our design is complete. That means
complete. Yes.
we are designing for a tension member.
Yeah.
Like a tension member is an angle section. We are designing for an angle section.
Right.
Now,
So I want to ask you, this angle member is always a tension member, or sometimes it is a compression member also?
It can be a compression member. It can be a tension member.
Correct.
Like in case of trusses, we are using like angle section only. Okay. So
In case of
truss.
truss, in case of a truss, for the roof truss.
Yeah, for the roof truss.
Yes.
So for the roof truss, there are various types of member are there.
Yes.
And some of the member will be tension and some of the member will be compression.
Correct.
Okay.
Yes.
In our structural analysis, we do that analysis.
So in a truss, the angle section is a tension member.
It may be a tension member. It may be a compression.
So how just by looking at it we decide, or there is a way to decide?
No. That is basically a different subject. That how you analyze a truss.
Right.
And it will be covered in structural analysis part. Okay?
Correct.
When we will read that particular subject,
Yes.
that structural analysis,
Correct.
and there we will solve
Yes.
different types of problem, that
Right.
how to analyze a truss, and
Right.
which members are basically tension member and which members are basically
Right.
compression.
I got it, sir.
Okay.
Yeah.
And here this is the design part.
Yes.
When we have already covered that, when we already know that
Yes.
in a truss there
Yes.
are mainly suppose 12 members are there,
Yes.
and 5 of them are tension
Yes.
member and 7 out of them are compression member. So now we know that these particular members are tension member and these particular members are compression member.
Yes.
And we also know
Yes.
that from that analysis that for tension members,
Yes.
how much load is coming on that particular members.
Yes.
Okay?
Yes.
For each member, how much load is coming.
Yes.
So to resist that particular load,
Yes.
we will design that member.
Yes.
Okay.
Yes.
So that is the analysis part,
Yes.
where we will just calculate that how much load is coming in a
Yeah.
member, and that member is a tension member or compression member. When we will know that a member is tension member or compression member, then we will design for that member
Yes.
that which section should be provided there
Yeah.
as a member,
Yeah.
so that it can resist that amount of load which is actually coming on that member.
What are we designing? Suppose it is a nut, it is a section and a gusset plate and a bolt.
Yeah.
Then what are we decide? We are designing the length of the section. We are designing the length. We are designing the diameter of the holes for the bolt. Is that exactly what we are designing to resist the load?
Yeah. That is basically, we will assume that
Yeah.
what is our gusset plate thickness, or what is our gusset plate thickness width.
Correct.
There is some minimum criteria. We will follow that,
Yes.
and we will use some diameter of the bolt
Yes.
related to our gusset plate thickness or gusset
Yes.
plate width.
Yes.
And we will first assume that
Yes.
the diameter of the bolt will be this, like
Correct.
M20 bolt will be used. Okay.
So when we are
for
designing, sir, we are also designing how much load, maximum load should be there. Beyond that, it should not go. Otherwise, it will fail.
No.
Okay.
For design purpose,
Yes.
always there will be some amount of load given to your question.
Okay. Okay.
Like in your question,
Yes.
that you sent me,
Yes.
see there it is written that factor load is something.
Correct.
Okay.
Yeah.
So factor load, how can you calculate the factor load? Where from this is coming? This is from the analysis part.
Okay. Yeah.
That you have analyze some kinds of structure,
Yes.
and there was a member
Yeah.
that was a tensor member,
Yes.
and for that tensor member,
Yeah.
like 200 kilonewton of load is coming. So as a engineer, what we will do?
Yeah.
We now actually know that 200 kilonewton load is coming on that particular member.
Yes.
So we will design a certain member
Yeah.
that can resist 200 kilonewton of load.
So we are designing the length of the thickness of the gusset plate and the diameter of the bolt holes.
Actually designing that which member we will use. Okay.
Yeah.
Like here.
Equal
we
angle.
will use
Equal angle section.
Equal angle.
Yeah.
Okay. So for equal angle, we
Yeah.
are suppose there are different type of equal angle sections are there in our steel table.
Yes.
But which table we actually use?
Yes.
Okay.
Yes.
Actually, which particular 1 minute.
Yes, sir.
These actually. Okay. So there are different members are given in your steel table.
Yes.
We have to take one out of them
Yes.
so that that particular member
Yeah.
can resist 200 kilonewton of
Correct.
load.
So we are also given that it is a equal angle section.
Yeah.
So in
there
equal
your
angle
question-
section also there are different types of equal angles.
Yes, there are different types of equal angles. There are different types of unequal angles.
Means the different types given in the steel table are the different width and all, I think, no? The different length and the different width.
No. Actually, this is not about length.
Huh.
Whatever given in your question
Yeah.
or in your steel table, this is about the section. No length is given there.
The dimensions of the section, no? The breadth and the width of the section.
Yeah, breadth and width of the section.
Means the thickness of the equal angle section, no? The thickness of the plate. Yeah. Length is not important, but the
length is not important.
no, but the thickness is important. The depth is important.
Yeah. Thickness is very important.
Yeah. Okay.
Okay.
So we have to decide of what width of what the dimensions of the section should be of the equal angle.
Yeah.
And the gusset plate is fixed. That we can't change.
Yeah, gusset plate is fixed.
Okay.
Okay, for the gusset plate, we will not actually design.
Yes.
We will design for the gusset plate for another reason.
Yes.
Like you have a column and you have to fix that column with the your footing. Okay.
Yeah.
So for that reason, we have to design your gusset plate separately. Okay, so that is different question. That will be a different
Correct.
question.
Correct. That is a different thing. Yeah.
Yeah, that will be a different.
Yeah.
In here, we will only design a member.
Yeah.
So how can we design? We will choose a member first from the steel table.
Yes.
And we will see that particular member,
Yeah.
whatever we have chosen,
Yeah.
that it is capable of carrying that amount of load
Yes.
or not. If
Yes.
can
Whether it is
carry-
safe or not.
Yeah, whether
Yeah.
it is safe or not. If
Correct.
it is safe, then it can carry more than that amount of load which is given in your question.
Yes.
Okay.
Yes.
If it is not safe, then we will choose another section again.
Okay. So I understood. Thank you very much. Yes, I understood.
Okay.
Yeah.
So here your design strength due to the yielding of gross section, which is given in this formula, that is TDG equal to AG into FY by gamma m naught. This formula we will use first, and then we are design.
Sir, could you tell me that formula again? TDG, no?
Yeah, TDG.
D and G. G is for gross section, D is for design, and
Yeah.
T is for tensile strength.
Here you see here the design strength of member under axial tension. Here D for design.
Yeah.
Okay.
Yeah.
G for gross section.
Yeah.
G for gross, and T means which tensile strength. T means
Okay.
tensile strength.
Okay.
Okay.
Yeah.
Under axial tension. Okay. This tensile strength means axial tension.
Axial tension means when the load is along the axis of the member.
On the axis of the member.
Yeah.
Exactly.
It can be horizontal axis or vertical axis.
Yeah. In case of process, if you see that there is only the axial forces are coming.
Correct.
No, you can say no lateral forces are coming there.
No lateral forces, and whether it is eccentric or centric also is important.
That is basically the compression member. That is the vertical member, or you can say the column.
Okay.
So there will be some eccentricity there.
Yeah.
We have to use that eccentricity.
Okay.
But in case of process,
Yeah.
if there is any kinds of forces acting on that any member,
Yes.
that should be axial. Okay.
That should be
That should be axial. That
axial. Yeah. Yeah.
forces forces should be horizontal kinds of force acting outward from your you can say the
It is
member.
pulling it, no? It is pulling
Yeah,
it.
it will pulling it.
Yes, sir. I got it, sir. I got it. Thank you.
Okay. So here you know that AG means the gross sectional area, okay, and Fy is your yield stress, okay,
Yeah.
which will be given in your question that which material you are actually using.
Yes, yes.
And gamma m naught, as I told you
Yes.
previously, that this is the partial safety factor which we are using when we are using Fy, that is the yield stress. For yield stress, we are using gamma m naught.
So gamma m naught, you're saying?
Yeah, gamma m naught. M naught means
Acha,
0.
gamma m1 is it? Gamma m naught.
Yeah, this is gamma m naught.
Okay.
You see?
So gamma m naught is how much, sir? Is it 1.1?
1.1. It is 1.1.
1.1.
Yeah.
Okay.
Okay.
Yes.
Okay. Now the second part is design strength due to the rupture of critical section. And for rupture of critical section, there is two parts. One is for plates. You can see here plates.
For rupture of critical section.
Yeah.
That was for yielding. That was for yield
No,
strength.
no. Yield strength is this much.
The first one
yield-
which you did was for
first
yield
one.
strength.
Yeah.
Yeah.
This is for yield strength.
Yeah. And now we are going for rupture.
Now, yeah. Now
Design
we are
strength for
going
rupture.
Yeah. So for rupture, you can see firstly it is subcategorized as plates. Okay?
Yes. Yes.
So for plates, we will simply using this formula.
Yeah.
But here we are using angle section. Na?
Yes.
So for angle section, we will not use this formula. For angle section,
Yeah.
here one more formula is given. Yeah.
Okay.
This is for your single angle section.
Okay. Okay.
So for single angle section,
Yeah.
this is your formula you have to use.
Okay.
You can see it, na?
Yes. Yes. I can see.
Okay. So this is the formula we will use
Yeah.
to calculate the design strength of the member due to the rupture of critical section.
Yes.
Okay.
Yes.
So here this ANC, this is the net area of the connected leg. So
Yeah.
here for a angle section there are two legs, as we are saying that if
Outstanding leg and connected leg, no?
yeah, outstanding leg and connected leg. One leg will be connected through the gusset plate,
Yes.
and other leg will be free.
Will be
Okay.
free. Yeah.
So one will be connected leg, another one will be outstanding leg.
Yes.
So here ANC, that is the net area of the connected leg.
Yes.
Okay, and here you see AG naught, that is the gross area of the outstanding leg.
Yeah.
Okay, and
Yeah.
you can see here that here we are using gamma M1.
That is AGO, no, sir? Not means zero, but this is O means O stands for outstanding, no?
Yes.
Yes. Yes.
AGO, you can see
AGO, because that others will confuse it with the other knot.
Yeah. AGO.
Yeah.
Okay, so this is the gross area of the outstanding leg,
Yeah.
and this is the net area of the connected leg.
Yes.
Clear?
Yes. Clear. Clear.
And here we are using the ultimate stress, that is Fu,
Yeah.
and for ultimate stress we are using the partial safety factor gamma M1.
Ultimate stress. Now we know the yield stress we already are going to get from the whether it is 415 or 250 whatever.
Yeah.
FY. But FU from where we will get, sir, the ultimate stress?
Fu for it is actually a constant value. If it is not given in your question, then Fu should be 400.
Okay.
Okay.
What should be?
400 Newton per millimeter square. It will be. It is a fixed value.
Uh-huh.
If it is given that your yield stress is 250 Newton per millimeter square, like
Yeah.
E250, your grade of steel,
Yes.
then your ultimate stress should be 400.
Okay. That is fixed, and that will be given in the question or in the steel table.
Yeah, if it is given that E250 your grade of steel, then your ultimate stress will not be given in your question.
Correct.
You should
We have to know it by heart.
Yeah, you have to know it that.
Okay. Got it, sir.
Should be 400.
Yeah. That means that is the ultimate stress that it can bear, no?
Yeah, that is.
That is 400 newtons per millimeter square.
400 Newton per millimeter.
And the yield strength would be 250 newtons per millimeter square.
250 Newton per millimeter square.
Got it. Yes.
Okay, one more thing.
Yes.
I'm telling you
Yes.
that this FU, this is basically what the material we are using.
Yes.
Okay.
Yeah.
So there are two things in our steel structure.
Yeah.
One is bolt, and second one is your plates. Okay,
Yes.
bolts are actually whatever we are using,
Yes.
that is also made of steel, and the plate we are using, that is also made of steel.
Correct.
That is, this single angle section, whatever we are saying,
Yeah.
this will be made of steel, and our bolts are also made of steel.
Yes.
So in our connection chapter, that is the first chapter,
Yes.
there will be there shall be the design of bolts also. Okay.
Yes.
But for bolts and for plates, the
Yeah.
ultimate stress should be different. Okay.
When you
So
say plate, you mean the gusset plate?
yeah, it may be the gusset plate, or
Yeah.
it may be the single angle section, whatever we are designing.
Ah, okay. It could be the angle section is also called a plate, and gusset plate is also called section.
Angle sections are made of plates, na?
Right.
We are saying it single
Ah,
angle, that
correct.
this is made of two plates,
Right.
is not it?
Yes. Welded together.
Yeah, welded together.
So, and the bolts are like screws, na?
Yeah, bolts are like screws.
Okay.
That is also made of steels.
Correct.
And if we say the ultimate stress, why I am telling you,
Yeah.
because for bolts,
Yeah.
whatever I am telling you, that FU, that is the ultimate stress, is 400 Newton per millimeter square.
Yeah.
That is basically for bolts. Okay.
How many millimeter square, sir? Which for bolts you said?
400.
400, yeah. FE 400, no?
Yeah,
No, you're talking about ultimate stress, correct.
Yeah.
That means FE 250, mild steel.
FE 250 you can say.
Mild steel, no?
Yeah. Okay.
Yeah.
Now, if it is given that your yield stress is 250 Newton per millimeter square,
Yeah.
and you have to decide what will be our ultimate stress.
Correct.
If you are going for bolt,
Yes.
design of bolt, then
Yeah.
you will take it as 400 Newton per millimeter square.
Yes.
Okay.
Yes.
But here we are not using any bolts. We are only designing a particular member, that is single angle section.
Yeah.
And the single angle section is not a bolt material.
Correct.
Okay.
Yeah.
This is a plate material. So here
Plate
we
material.
will not use that 400. Here we
Yeah.
will use 410.
415, no? 415.
410.
I
Not
see.
415.
Usually-
For 41,
usually
we are using 415. That is for our IS 456, our RCC structure.
Correct.
Okay.
Yes.
Here in our steel design,
Yes.
we will use 410.
410. Okay.
Yeah.
Yes.
Yeah. Here it is 410. So
Okay.
you just write it in your notebook.
Yes.
That for bolts it is 400 Newton per millimeter square, and for plates it is 410.
Yes. For plates, yeah. For plates,
FU,
F
because it will not be given in your
FE 410 for plates.
Yeah, for plates.
And for bowls, it is FE. It's mild steel. FE 250.
No. That is the yield stress. Yield stress is always 250. Yield stress will not change. This ultimate stress, FU value.
Ah.
Okay. This FY value is always same. It is 250.
Acha, we are using that FE 250 only for. We are using mild steel only for bolt and for plates.
Yeah.
But FU will change.
FU will change.
Why,
For
sir?
both,
Why it is changing? FU?
This is actually the manufacturing value. Whatever
Right.
we are using in our.
Yeah.
That means this is actually fixed thing, na?
Yes.
Which are actually in our factory. It is just manufacturing.
Yes.
And this is some fixed value as per our code.
Yeah.
It is actually manufactured.
Yes.
So there is no change in the value. Whenever we are using any bolt,
Yeah.
so it will be manufactured as per our codal provision.
Correct. But are they using the same kind of steel for bolt and for plate?
Similarly, you can say that we are using same kinds of, but
Yeah.
there is some, you can say that material.
Yes.
When we are using bolt material,
Yes.
like there we are using maximum parts of steel,
Yes.
and there may be some kinds of carbon percentage,
Yes.
and there will be some kinds of magnesium percentage.
Correct.
So these are the things
Yeah.
that will vary a little amount
Yes.
for the manufacturing of your plates and
Yes.
your bolts.
Correct.
Okay.
Yes.
For that different value,
Yeah.
there will be some change in the ultimate stress.
Yes.
Okay.
Yes.
So this is the codal provision that is actually manufactured in our country,
Yes.
and we generally go with this particular value.
Yeah. Yeah.
You understood, na?
Yes, sir. I understood.
So this is is your ultimate stress,
Yeah.
and this is your yield stress.
Yes.
And here comes another thing, that is the beta. This
Yeah.
beta value is something
Yeah.
different.
Yeah.
And this for beta value,
Yeah.
this formula is given as per your code. Okay.
Yeah.
This is the formula you have to use. And here, so many things are there.
Yeah.
One W is given here.
So what is beta? What is beta?
This
This beta value is what?
This beta value you can see here.
Yeah, I saw it. I saw it. But what does it signify?
This is signify actually that you are using the gross outstanding area
Yeah.
of your section.
Yeah.
And for outstanding area, we are actually what we are doing, that in your net area.
Yeah.
This is your net area, and for net area, what it is doing, we are applying 0.9, because for that cutting portion of your plate, some kinds of you can say that strength of that particular plate is reducing. That is why we are using here 0.9.
Yeah.
But here, if we see that this part,
Yeah.
there is no reduction in your plates.
Yes.
Okay, that means there is no holes due to the
Correct.
due to your
Correct.
bolt.
Yes.
Okay.
Yes.
We are not using any kinds of bolt here.
Yes.
So there will be some factor
Yeah.
which will decide that this value,
Yeah.
that due to the outstanding part,
Yeah.
the strength of that particular angle section will reduced, or it will be induced, or it will be greater than a normal value.
Okay.
That will basically decide this beta value.
So
Okay?
that is a
And
fixed value. The like your gamma, that beta is a fixed value.
yeah, beta is a fixed value, you can say, when this parameter will be induced in this formula.
Yeah.
Okay, there are different parameters now. That is the yield stress of the.
And what is
of
beta
steel.
defined as?
Beta defined as, this is a constant value.
It's a
There is-
constant. It's a constant.
Yeah. You can say this is the constant value. If you can named it is, then it might be written here. Otherwise, you have to consider it as a fixed value.
Okay.
Okay, a constant value. Beta
Okay.
is a constant, you can say.
Yes.
Okay.
Yes.
Okay. So here 1.4 minus 0.076, this is W by T. Okay.
Yes.
And now what is this W? You can see here, this is your W. Okay. This is your single angle section, na?
Yes.
You can see this is the single angle section, and this part is this below.
So what is a
part
single
is-
angle? We are only studying single angle sections. We have not yet done double angle sections, no?
Yeah, but you are not using double angle section, only single angle section you have used.
Yes.
Yeah, actually we can use that double angle section.
Double angle means it will be a U shape.
No, it will not be a U shape, but it will be like T shape.
T shape.
Where,
Huh.
yeah, T shape, inverted T shape.
Inverted
That
T
means it
shape.
will be just
There
in
are two
this-
angles. There will be two angles.
two angle back to back.
Back to back.
Yeah.
I got it, sir. I understood.
In that case, we can use two angle section.
Yes, I understood. Yeah.
Okay. So here, this is your W value. That is your outstanding leg. Clear, na? This
Yeah.
is your outstanding leg, and this is W.
Yes.
And your T is your thickness of the angle section.
W is the W is the
Width of the outstanding leg.
width of the outstanding section.
Yeah.
And
This is
T
your
and T is the
T is the thickness of your angle section.
T is the thickness.
This is the thickness. You can
Thickness
see here, T
of
is-
thickness of outstanding and connected leg will be the same.
Yeah, it will be same. It will
Okay.
be same.
Okay.
It will be same.
Now,
There will be
since
no
this
change in the
is since this is equal angle section, the W will be the same for outstanding, and for connected leg it will be the same.
Yeah. If it is the equal angle section, then it should be W.
Yeah.
And in this portion, it should be again W.
Okay.
That means if I am telling you that it is a ISA 100 into 100 into 6,
Yeah.
that means your 100, this 100 millimeter part will be in outstanding portion as
Yeah.
well as in your connected portion also.
Okay. The whole length of that connected leg is also W.
Yeah.
Okay. The whole
For equal
length.
angle section, it should be W.
Okay.
Clear?
Clear, sir. Clear. Thank you.
Okay. Now here it is Fy by Fu. You already know that how you can calculate this value. and
Yes.
then it is bs by lc. Again bs is a constant value which is depending on your section,
Yeah.
and here you can see that this bs formula is given. Clear, ma'am?
Yes, yes.
That is w plus w, it might be 1 or l, you can say w plus w1 minus t. Okay,
Yeah.
so this w is the
So why
width of the
W1?
outstanding leg.
W1 is what is W1?
Yeah, I am telling you,
Yes.
this w1 is basically, you can see here this black portion, this is basically the your uh, this side is the connected leg na? So this is
Yes.
your bolt line. In this line the bolts are actually used.
Acha, under
Okay,
that is the gusset plate, no?
under that this is the in gusset plate
Gusset
in,
plate. Got it.
yeah, in dotted portion.
Yes,
This is
yes.
the gusset plate.
Yeah.
Okay, and from this point
Yes.
you can see that from these two from this, you can say a corner point,
Yes.
from this corner point to the bolt line,
Yes.
this distance is basically w1.
Got it. Got it, sir.
Clear?
Yes, clear.
Okay, now mine w plus w1 minus t. T is nothing but the thickness of your angle section.
Yes.
Clear? So
Clear.
if you know these three value, then you can calculate this bs value.
Okay.
Okay,
Yes.
so here it is bs divided by lc.
Yeah.
This lc is basically the length of the connection.
Yeah.
Okay, so you cannot, you can imagine it here, but when we will draw these things in plan, then you will understand that how can we calculate this lc. Lc is basically the length of the connection. Maybe you can imagine that this is your bolt line, and how many bolts you can see here?
One.
One. But this is the bolt line. From here you are just seeing the cross